let's start from introducing myself. So, even though I think we spoke in a few occasions already with almost all of you, so, and my office is just, you know where, in the math corridor, and I'm always ready to talk to you whenever you, the worst that can happen is that you come, I'm busy, and we fix an appointment, okay? But please, actually, in fact, I think it will be very important that you interact as much as possible with us and with me for sure. There's no more light here. Okay. So what is the course? The course we are starting, it's about differential geometry, but differential geometry has a long history. So in fact, the first part should be really called surfaces in R3. Okay. So the idea of a differentiable manifold was born at the end of the 19th century, and it was formalized around the same time of general relativity, more or less. So it's about 100 and something years old. But there are 200 years before of history of studying surfaces and hypersurfaces in Euclidean spaces, which basically contain the fundamental ideas of what differential geometry should have been afterwards, okay? So the idea is to have around 12 lectures, more or less, on surfaces. For some of you, and now in fact I'm going to ask you a few questions, because for me it's important to know how many of you have already seen this part of the story. And then with this material in our bag, we move to the real differential geometry, okay? So, yeah, actually, in order to tune my course, it would be nice to know how many of you have seen already, well, it's even possible that some of you have seen the whole picture, so even the real differential geometry. But for example, how many of you have studied a little bit the theory of surfaces in R3? How many of you know what is the Gauss curvature of a surface, the mean curvature of a surface?
I use the Locarno book.
With the Locarno book, which is the standard reference.
I have studied a little in general.
So you started from the end backwards.
Yeah.
Okay. So you started from the definition of a Riemannian manifold. And so 3 people who know what is the Gauss curvature of a surface in R3. Nobody has entered the room now, so okay. So okay, 3 of you. So maybe for you, you should think of the first part as kind of a review. And if it's too much of a review and you get bored, come to my office and openly say, Professor, I'm bored. Okay? And I'll give you something to integrate. Okay? I don't want you to just stay there and waiting for something interesting. Okay? I can give you right away something interesting from the beginning, and we can talk in my office. Okay? So, okay. Actually, the whole point, the major difficulty in differential geometry is actually the first lecture, because it's what is the definition of a manifold. Okay? So differential geometry is part of geometry. We study spaces and special spaces, and we want to classify them, as every other type of geometry want to do. Topologists study topological spaces, and they want to have classification theorem. I mean, a topological space with this, and this property is this. I mean, these are the most beautiful theorems in geometry you can think of. An algebraic manifold with this property is this. Okay, so the differential geometry does the same, but now the object in question is a different kind of spaces. I mean, every type of geometry studies different type of spaces. Okay, so and the difficulty is actually defining the space. Okay, well, actually, then the difficulty is also proving the theorems. Otherwise, we would all have Fields medal. Okay, but for the students, I mean, at the beginning when I was sitting in your chairs, I mean, I remember when I saw actually, I didn't have the surface part done before. My professor threw on the blackboard the definition of a manifold, and we stayed there for 2 months, essentially, because it's completely crazy what you see, okay? Everything, and what is the idea? The idea is that, in fact, what should be told, and that's the spirit of the first 10 or 12 lectures, is to teach you how to, because actually we will not cover the whole of differential geometry. So basically every concept in differential geometry is imported from what we do naturally in Euclidean space, without even thinking. That's the point, is that in Euclidean space everything is so simple that without thinking you make many operations. You translate, you move, you rotate, you take scalar products, you can even multiply vectors, okay? It's obvious in Euclidean space, it's even almost obvious. I mean, it will take us 20 minutes to define properly what is the tangent space to a set with sufficiently high regularity, okay? While for a differentiable manifold, you will see the definition of a tangent vector is a mess, okay? So that's why I will overemphasize when we study things in Euclidean space, what are we actually using in Euclidean space? I mean, if the aim of the course was to teach you how to handle subspaces of Euclidean space, I could go much faster than what I will. But I will slow down to notice at every step what I'm really using. Because the problem is that the Euclidean space is everything. It's a group, it's a vector space, it's a module from algebra. It has all the structures all at the same time. And whatever problem you are studying, you are using one mixed with another. And then when you end up working on something which is not Euclidean, you really have to remember, in the Euclidean case, how did you solve the problem, which structure did you put to solve the problem, and how you used it. Okay? So that's more or less the spirit. Okay? And in fact, I mean, this is even to justify, but I'll try to be this year very, very quick, because actually the real beginning is not even surfaces. The real beginning of differential geometry is curves. In geometry, we grow by difficulty, and difficulty typically, not always, but typically means dimension. Okay? So lower dimension is supposed to be easier than higher dimension. This is not even always true, depending on the problem. But I mean, clearly, and actually you don't even know what dimension is. Actually, even the definition of dimension for a topological space is quite subtle, okay? But intuitively you know, I mean, so a curve should be something of dimension 1. I mean, a point should be something of dimension 0, a curve of dimension 1, and a surface of dimension 2, and then you build on this, okay? So the first thing is, what is really a curve? Now, oh, by the way, still preliminary, as your colleague said, I mean, there's a standard reference. I mean, I think everybody in the world studies this subject. I mean, the first part of the course, I think everybody studies on the book of Doccarmo. Because, of course, there are millions of books, and you are free to choose the one you prefer. I mean, whichever book contains in the title the word surfaces, I mean, differential geometry of surfaces, whatever, I mean, it's certainly good. But there is a book by Doccarmo called Geometry of Curves and Surfaces, which is the standard reference for everybody. And I will use it. Okay, so first type of sets that we are interested in are curves. And then, I mean, this I'll try to do the least possible times, but I'll throw on the blackboard the answer. I mean, what is a one-dimensional space, basically? That's what should be a curve. And now, so let me give you what historically has been agreed to be the answer. So, a differentiable curve is actually a map let me call it alpha, and just a quick comment, I will describe a little bit the theory of curves in R3. If you want to describe the theory of curves in R27, go ahead, no changes, okay? So where I, for me, is just an interval, and actually this could be finite or infinite, I don't care. I mean, A and B could be plus or minus infinity, there is no problem. And alpha should be, so if given the fact that I said differentiable, alpha is already supposed to be smooth, okay? And again, you can lower the regularity. I mean, if you want, actually, strictly speaking, differentiable should be C1 maybe. We don't care, okay? In very, very few places it will be different to study C1, C2, C3 objects, okay? In that case, I will specify. Otherwise, everything is supposed to be infinitely differentiable, okay? I mean, just to fix notations, what does it mean it's differentiable? I mean, this is a map from an interval to R3, so you can take the calculus book. And in the calculus book, but also the topology book, so I'll try to call very often the parameter on the real line t. So alpha of t will be a vector in R3, so will be a triple of three functions. Okay. And smooth, of course, means that each of them is smooth. Okay. So both three functions are smooth. All three functions are smooth. And then, so this is a differentiable curve, and what is a tangent vector to a curve in R3? It's just the vector built with the first derivatives of these functions. Okay, so alpha prime of t, I'm writing just because I'm fixing notations, okay? I'm sure you know all this stuff. So this is x prime of t, y prime of t, z prime of t. This is the tangent vector to alpha at the point alpha of t. Okay. And just the last word in definition, alpha, a curve, so a differential, and actually from now on I will start. Otherwise, differentiable, okay? Differentiable curve alpha is called planar. I mean, from time to time it will be convenient to have this word in our bag. So it's planar if, instead of going in the whole of R3, there is actually a plane, if there exists a plane. A plane, okay, I'm not asking that this is a two-dimensional vector subspace. Huh? I mean, it's not supposed to pass through the origin. It's really a plane, an affine plane in R3. Okay? A plane P in R3 such that alpha of I is contained in P. Okay? Now, typically, every time the curve is planar, as I said, P is not supposed to be, for example, a vector space, so it's not supposed to be passing through the origin, but by a rigid motion of R3, by a translation, I can translate it, you know, to have something parallel, and a parallel plane passing through the origin. And then I can also use rotations in R3. So whatever plane this is, P now translated to the origin, I can rotate the XYZ axis in such a way that the normal vector, so how do you give me a plane in R3? You give me passing through one point. Which data do I need to know P? I need to know one point and one vector, the normal vector. Once you give me this, there is only one plane passing through that point with that normal vector. Okay? So passing through the point, I kill this freedom by translating into the origin. I'm saying, okay, I suppose that this passes through the origin. And the normal vector, I can use rotations of R3. I can suppose that the normal vector is always the 0, 0, 1, for example, the one pointing up. Okay? So basically, up to, the moral of what I said is up to a rigid motion of R3, which is a combination of translations and rotations. Actually, there would be also another one, strictly speaking, but I'm not using reflections. No? Reflections is the missing rigid motions that I'm not using. But in any case, up to rigid motions of R3, P, I can assume that P is actually the plane Z equal to 0. Okay? So in that case, it means since the curve will lie here, it means that alpha of t is actually not really a triple. One coordinate is killed. Okay, so sometimes I will just write this. So don't object that this is not a point of R3. If I write this, it means I'm thinking of this point of R2 as sitting in R3 in the z equal to 0 plane. Okay? Just to be quick. Okay, so that's the definition. But now comments, because the thing, I mean, you are grown-ups, so every time you see a definition, you have to question the definition. I mean, why this should be a good definition, if it's a good definition. Why does this answer the problem? I mean, we wanted to define something which we wanted to call one-dimensional objects, okay? So the one dimension somehow is, I mean, even though this would lead us to some subtle problem that I'm going to avoid, I mean, it's contained in the fact that here there is one, okay? So I'm taking a piece of the prototype one-dimensional object and I'm sending it somewhere else, and presumably this will describe again a one-dimensional object. This is far from being obvious because you know these kind of strange examples, for example, of continuous maps from the real lines to the plane which are dense. No? I mean, so when you have something dense, you say, well, but which is the dimension of this object? But in any case, okay, let's avoid this. But then, what kind of freedom and what kind of rigidity does this definition allow us? So, for example, because of course, I mean, we are thinking, this is what I would say is a kind of a physical definition of a curve. Because you see, I'm thinking of a curve actually not as the set, and this is the important, this is actually the whole point. When a geometer thinks of a space, thinks of the set. So I'm thinking of this. Okay? But this information actually, so strictly speaking, the drawing is not the curve. The curve is a map. So it's not just the image. So what I wrote here, what I drew here is alpha of I, which is much less than alpha. I mean, one thing is to know the map, and one thing is to know just the image. Okay? So this is, in some sense, the physical definition of a curve, in the sense that actually it comes with a parameterization. So the same set can be parameterized in many ways. Okay? Think, for example, when you think of this thing, you should build your simplest example. I mean, the real line, of course. In fact, so this is what? This is T00. This is the most stupid parameter. I mean, why I'm saying the real line is this? Well, because I have some kind of filter in my brain which tells me choose the simplest. Okay? But this object here is also what? Arctan. So if lambda is a new parameter, no? Why not? Or pick any map, surjective map from R to R and put it here. So it can be as horrible as you want. Okay? Which is the most horrible function that you know. Well, this is actually is not too horrible, especially because it has a physical meaning. What is the image of this map? Now I'm thinking, of course, when I don't say anything, I'm really thinking I'm taking the maximal interval where this is defined. So in this case, for example, it would be the whole R. So my interval I is actually the whole real line. Okay. And what does this parameterization do? I mean, starts from here, and then starts doing like this. It's kind of a pendulum which is growing in amplitude, no? And goes to infinity, which is actually, it's horrible, but it's nice, so it's not too horrible. Okay. So you see, this curve, these three curves are three different curves, because these are three different maps. So this is the typical mistake. I mean, this is the typical, actually, is the point of this definition. Don't confuse the geometric image with the curve. The curve is much more than a geometric image. It's how you move, how a particle moves on this space. Okay? Good. First thing. And then you say, well, but now intuitively, I think it would be difficult to agree because we don't know how to phrase it, but we would like, we have some kind of intuitive picture, idea of what it means to be a smooth curve. Here there is written something, a differentiable or smooth. I mean, these two words are equivalent, okay? A smooth curve is somehow a differentiable map. On the other hand, I have some kind of intuition of what should be a smooth space. Okay, so let's check. Is this definition compatible with these two ideas? Smooth space should be no corners, whatever that means. Okay? Well, so observations. One, this definition allows, for example, one type of, I don't know if you would agree to call it corner, but the definition allows something that a priori was not obvious. For example, self-intersections. So what do I mean? I mean, I'm sure we all agree that a particle moving like this would be a smooth curve. Yes. But something like this, do we allow it to be a smooth curve or not? Because strictly speaking, if smooth means I have a tangent space, we'll come to that, but I mean, you already know. Here there is a problem. Here there is no tangent space. Okay? But actually it's a smooth curve. Or, I mean, sufficient. I mean, if I can parameterize it well, it's a smooth curve. And actually, I could have left the picture because, okay, here's one example. I want to go quick, so I leave you for exercise. Oh, actually, every couple of weeks you will get a homework. Okay? The idea is that I don't care how you do it. You want to do it all together in groups or whatever. These are not marked. It's for you. Okay? So they don't enter into the evaluation of the final exam. It's for you, and there will be, of course, tutorials where you can discuss this and other things. Okay? For me, if you want to use them for, I mean, I think the point is, you are here, you have been passing through many selections, so I don't have to teach you what does it mean. Of course, the idea is that at the end of the course, you should be able to do exercises. The way you decide to reach this point, I mean, if you want to do in group, I have no problems, okay? The problem is that each of you should be honest with himself or herself and decide whether he or she is able to do the exercise, okay? So, in any case, for example, first exercise, draw this curve, okay? Okay, of course, the answer should be something like this, otherwise it would be completely, okay? But just to put it in the right position. So, technically speaking, all this was just to say, notice that in the definition I never asked alpha to be injective. So the point can pass through a point where it has already passed. Okay? So notice that in the definition there was absolutely no need for injectivity in order for, okay? But, I mean, this was kind of obvious. I mean, given now that you have noticed, now that I told you that there was not the word injective, these examples become obvious. What is less obvious, it can have corners. And this is a bit more strange, because somehow we are speaking about smooth curves, but the set where the point is moving can have corners. And this is the prototype, and it's actually very simple. Once you think that this can happen, you can even do it with polynomials. You see, the components must be smooth. So I cannot put very strange functions here. Okay, notice, these are all, up to now, I just used polynomial functions. Okay. But actually the set that they describe is bad. Okay, so again, here Here there is, I mean, it's pictorially obvious that this is horrible. It's technically a bit more subtle, I mean, because you might object back, well, but this object, even if it's horrible, this has a tangent space. There is an obvious notion of tangent space at this point. I mean, should be this. Okay. So in which sense this is horrible? Well, it is horrible because if you think of the particle moving, of course, it is true that this becomes a tangent space. But if I'm moving from the left, I will get the tangent vector oriented pushing down. While if I want to start and move to the other branch, I have to start immediate. So there is a discontinuity in the tangent vectors. Okay. So it's not really the fact that the tangent vector does not exist, but it's that you cannot move it continuously on the, okay. And then a slightly more sophisticated observation. You might say, well, the image of the curve in R3, after all, we are restricting ourselves to smooth functions. So is the image as a topological space? Now, look at alpha of I. Now we are in R3, and we have this object moving around R3. Very good. As a topology, so it gets a topology, because it's a subset of R3, which has the standard Euclidean topology, for example. So is this object homeomorphic to the interval where it comes from? So this is the image of some interval. This is the first step in thinking of classification. So we say, topologically speaking, curves are all the same. And are they all the same? Are they all equal to the interval? So is alpha forced to be, for example, an homeomorphism? Even, okay, there was one problem. If it's not injective, goodbye. Suppose it's injective. Okay, let's remove this obstruction by hand.
We can have a circle, right?
Okay, you can have a circle, for sure.
And therefore, there are at least, because the circle is compact, but...
That's a good point, because if you take a circle, of course, the circle, this is the typical problem in discussing these kind of things, because the circle is just the image. But, okay, we are assuming that we are going via uniform motion. Now, if I want to have an injective map, it means I'm thinking of a map from an interval which has 1.1, okay. It's closed on one side and open on the other, because I have to open it up, okay, to have it. But this is not an interval in this sense. Here, notice that this is, so actually there is no way, so this is not allowed. I mean, if I want to have a one-to-one map, I need to do this. But this is not allowed, so it means I have to go a little bit on the left. But if I go a little bit on the left, the map will never be injective. Okay, so that's one, but there are even more subtle situations. For example, again, I give you only the exercise, alpha. Now I pick this interval, and I go to R2, okay, R2 in the sense of the planar, okay. I don't need the third dimension. Oh, also here, notice that I've already, these are all planar, I mean, the third coordinate was actually 0. And if you take t going to 3t over 1 plus t cubed, 3t squared over 1 plus t cubed, for example. And again, actually, for your curiosity, this is an algebraic curve in the sense that this satisfies this equation. Okay, just for your curiosity, if you take this cube plus this cube, you get 3x. Okay, it's just to connect with another course that you are attending, or you are.
As it starts moving.
End of this one. Okay. So this is an algebraic curve in any case. These functions are smooth because actually I removed -1, which was the only problem here on the denominator. So these are smooth maps. So why should be this interesting? Well, let's understand it together. This one maybe I don't leave it as an exercise. Let's do it together. So what is the, of course I'm not going to draw it very carefully. So what are the main, so where does it go as t go, let's look at the limits and let's look at something, so for t going to infinity, where is it going? Plus infinity. Well, these are our positive numbers at that point, on that region. So it comes from, it lies here, somewhere here, but for t going to infinity, of course, t cubed kills t and t squared. So this goes to 0 and this goes to 0. So for t going to plus infinity, this curve is coming from here, from somewhere, and is going here, in the origin. Of course, it will never reach it, but the limit will be 0, 0. Okay? In this way, if you want, sometimes it's useful to put arrows on the curve to remember. For t going to -1, what is happening? The point is that, of course, for t going to -1 from the right, now this blows up. This goes to 0, so 1 over blows up, but blows up from the positive. Okay? So, and this goes to where? Goes to -1, of course, to -3. So -3 divided by, what I'm saying is that I have to erase a little bit of this equation, but it comes from here. No? So x is positive. It's positive infinity. Okay? And y, again, is positive infinity. So for t going to -1, you actually, so since this is my left point, it means the curve starts at infinity, infinity, goes down, and then I don't know what happens exactly, but at plus infinity it's back here. And I'm saying back because, of course, for t equal to 0, I notice immediately just by looking that at t equal to 0, this curve passes through the origin. So whatever. Now here there is a mystery box. Of course, I'll draw you the right one. You can ask the computer to draw it. I don't want to take first derivative, second derivative. Now I should study convexity, concavity. I don't care. Okay. But the truth is, pass through 0, makes a little loop and goes back. But remember that here goes back in the sense of a limit. Okay? So why is such a curve relevant for our observation? Remember, the question was, is alpha forced to be an homeomorphism? Well, actually, you can check it immediately. Alpha is injective now. That's the difference between all the other examples you can build, like, okay? So this is injective. So you might say, well, an injective differentiable curve is an homeomorphism. And this is the counterexample. One counterexample. But do you agree that this shows that this is not an homomorphism? Who finds the killing argument?
Every neighborhood of 0 has this threefold thing. It has branches, which is not homeomorphic.
Of course, yes. Of course, the only strange thing happens here. So let's look around here. A neighborhood of this point in the image. Now we are comparing two topological spaces. The interval -1 plus infinity with the Euclidean topology, and alpha of I in R2 with the induced topology. Of course, we have nothing to say about the topology here. This is the Euclidean topology. And this point corresponds to 0, we know. The origin here corresponds to t equal to 0 via this map. Okay, so what your colleague is suggesting is look at, so how do I understand the induced topology of a topological space? I take open neighbors of the ambient space and I restrict it to the subset. So I take a basis, I take disks, I intersect, and what I get is something like this. So now the open neighbors, now if I draw them straight, I have an interval plus an open interval which ends somewhere in the middle. Okay? Okay, your colleague is claiming, and this proves that this is not an homeomorphism. Why?
Because if it were homeomorphisms, then all the neighborhoods of it should be homeomorphic to the neighborhoods on the intervals, which are like intervals. Like, but this is not. It's not. This is not.
This is not connected.
Yeah.
The intervals.
Yeah.
You think this is not connected?
Yeah, I think it's not good.
Mm-hmm.
Because this loop goes to 0. So maybe if you draw it like an intervals, there is like kind of interval which contains this is thick and maybe the
My
other
feeling
one
is that
also-
this is actually connected in this topology.
Okay.
How can I disconnect? I mean, of course, I think I mean, this piece here is actually connected to this, even if it doesn't touch. Because I mean, if it's disconnected, I should be able to write it as the union of two open non-empty sets. Okay? And of course, I'm sure what you have in mind. This and this. So the problem is, are they open? And this one is open, because I can separate. But this one is not open, because whatever open neighborhood I take, I will take another little bit of this. So, I think you were hinting already to the answer. I mean, you know, how to prove that those things are not homeomorphic? Typically, I mean, this is usually a very hard question. So either you are lucky or you are desperate, okay? So, lucky means there is a point. If you remove a point from one side, there is no other point on the other side which does the same. I mean, if either these tricks work or it's a mess.
So maybe you can.
But I mean, here, why don't you remove this point here? And now you see my objection collapses. How many connected components have this object here?
3.
3. And the number of connected components is a topological invariant. Okay? So here I get 3. While any other point, now the point is, of course, I don't know which point should be on the interval. Whatever point on the interval I remove, I will get 2.
Also, the inverse image of this should be. The inverse image of this should be 2 intervals, not 1 interval.
Okay, now of course, once you know, you can reformulate everything in many ways. Okay? I mean, just to say, so these are kind of warnings, no? Because the definition seems so innocent that they say, oh, okay, what are we studying? The most beautiful curves. Well, yes. Yes, from the point of view of which maps parameterize them, yes, these are the most beautiful maps. In terms of geometric sets, they could be pretty strange. Okay? So, now, yeah, I don't think we need it. So these are kind of strange. So I started from the pathologies, and now let's write down something non-pathologic, okay? Of course, which are the simplest curves that, I mean, the simplest curves that we want to study for sure. I mean, okay, straight lines, circles, variations, ellipses, whatever. I mean, all the curves that you know must fall into this category. So, for example, again, this is just quickly to fix notation. Examples, but now with nothing strange. So when we will say straight lines, the point is that I have to tell you already the parameterization, not just the image. Okay, so that means alpha of t, of course, is equal to what? Is some vector plus t another vector. Okay, so passing from one point with one direction, that's a straight line. From time to time I will emphasize the fact that these are vectors, underlining them or something like that, but I mean, these are just vectors in R3. Okay. circles. Again, I mean, we have millions, I mean, infinitely many parameterizations, but which is the most physically famous parameterization of a circle? But for a circle, of course, you have to give me a center and a radius, okay? And once you give me this, so you give me a center, and then you give me a radius, and then let's assume that we want to move uniformly at uniform speed, okay? Which is actually was the same moral for the straight line that we use. Now the speed here is constantly equal to v, to the norm of v. So, but now here you will understand today, probably at the end of the lecture, why I'm doing something not the simplest thing. Okay? So where? What? C is a point in R3 in, oh sorry, this is, of course, okay, because a circle, so I'm writing the parameterization assuming that the circle lies in the z equal to 0 plane. If you want it to another plane, you have to take this and transform it. So C is a vector, C is the center, is a point over 2, R is a positive number, okay? Okay, cousin of, I mean, just to have one other example in your mind, circle, and also to move a little bit, I mean, these are all planar curves, so let's have something that invades a little bit more the space, okay, just for, so alpha of t, say anything, it's really always understood that t lies in the largest possible interval where the functions are defined. In all these cases, it's r. Okay. So, in both cases, both in this, in example 2 and 3, you can object that I didn't write the simplest thing. I mean, which was the point of dividing by r? After all, t and t over r moves in the whole real line. So, this curve and this curve actually are the same, have the same trajectory. Okay, you will see. I mean, this is just for and also here you can make the same objection. I mean, t over the square root of and t, they describe exactly the same thing. Okay, but again, it will be useful for later computations. Okay. Just to, have you all seen in your life a circular helix? I mean, here, this is just, I'm writing just to have you starting getting some feeling of what's the story. I mean, how do I imagine? I mean, I cannot, of course, nowadays I can always ask a computer to draw it, but I mean, it's not the right thing to do. I mean, you should have a feeling. I mean, how do I understand a little bit a curve? So, of course, this is quite simple, but I mean, you see here, of course, the observation, if I want to understand how does this look, I notice that if there was not the z coordinate, this was just a circle. I mean, the center would be the origin. I have to adjust the radius in some sense. No, because it's not exactly in this form, but I mean, certainly I can transform it to something in that form. Okay? But actually the radius is a, of course. But there is the z coordinate. So if this was constantly equal to 0, this was just a particle moving around a center. There is this z coordinate. So what is the effect of the z coordinate? That this point, this particle, while it rotates around the center, it actually moves, and now depends on the sign of b, whether it's positive or negative. Oh, sorry, a and b are just the parameters, they're fixed real numbers, okay? So if b is positive, for example, while this rotates around, this goes up. Okay, so you are cutting a circle and you are stretching it up. Okay, at uniform speed again. Okay. Just to have a little bit of feeling, I mean, before asking a computer. Okay. Now, okay. Okay, and we will build more examples later. Okay, now, what is actually the only, unfortunately, well, essentially the only intrinsic geometric property that we can study on a curve? Well, its length. Okay. So the only geometrically meaningful, almost the only geometrically meaningful, I mean, we have one notion of curvature essentially. And I mean the whole black curve. Now, what is the main problem is how to define the length of a curve. This is usually also part of calculus courses sometimes, I mean, depending on where you stay. So, do you all know how to compute the length of a curve? Good. So, I'll skip many details. I just remind you the idea because it will be useful for later. Now we have this curve in R3. We take a piece, a compact piece. So the image, let's say we take the piece between here and here, where this is alpha of A and this is alpha of B. So what I mean is that I'm assuming that the interval, and actually I'm moving from left to right. AB is contained in the interval and alpha is a curve from I to L3, okay? And the question is, how do I compute the length of the piece of the curve between A and B? Okay. Now, okay. The idea is to make the curve as close as possible to a bunch of segments. Okay. So, because of course, first guess. Well, I compare the length of the curve with the length of this segment here. I take alpha of A, these are 2 points in R3. I measure how far they are from each other, and I say, well, this is the first approximation. This is, of course, a disaster, no? Yeah. I mean, nowhere close to the final answer. But then you start saying, well, okay, but this was too rough. Let's put few points in between. Okay? And then, instead, I say, well, the length of the curve should be closer to what? To the sum of the lengths of the segments between two consecutive intervals, endpoints of the intervals that you have selected. And so on and so on. And at the end, you take the limit. Okay? So, mathematically speaking, what do? We take a partition. Now, P is not a plane, it's a partition. Starting from the first extreme, less than 1, less than 2. Okay, you take a partition of your domain, and then you define the length between A and B of the curve alpha, subject to the partition P, to be the sum where this symbol means the length of the vector in R3, okay? So these are not numbers, these are vectors. Okay. And then you also define the norm of a partition. So the norm, again, some kind of absolute value in the space of partitions, to be the maximum of the distances between . And now this is the absolute value of a real number. Okay? My students have to be ready to jump. Okay? I'm not going to invent symbols and things. I mean, the same symbol means the only thing that makes sense. Okay? And then what is the, since you all shake your head saying yes, that you know this story, I'm just telling you which are the milestones. So now you have a definition of the length subject to a partition, a definition of a norm of a partition. So now, of course, the only question is, can I take the limit of this object here as this goes to 0? Because I'm getting more and more interested as many points I put on the thing. Okay. And the point is that, of course, the classical observation, which is actually a theorem, is that for any epsilon there exists delta, such that if P is less than delta, if the norm of the partition is less than delta, then actually not just this converges to something, but to what? Okay. So the length between A and B of alpha P converge, I mean, I'm going to say something minus something is less than epsilon. So where does it converge? To the formula that we use. Okay. I'm not going to prove it. You said you knew it. Your fault? No, it's okay. I mean, it doesn't contain anything interesting for us. It's an application of calculus. I mean, this is calculus in. Okay, there's nothing geometric here going on. So I'm not going to give a proof now. But this is answering what should be, at least, I mean, this is kind of a constructing a definition. Okay? Looking at the picture, I think I know what I want as the definition of length. And this theorem is telling me what it should be. So this object here is the limit as P goes to 0. So this should be what I want. So definition. The length of alpha between, actually, let's say directly, of alpha of AB is this object here. Okay?
What if we work with non-differentiable curves? In this case, we wouldn't have the derivative of alpha, right?
We wouldn't have the derivative of alpha.
Yeah. In this case, can we always also find? I know there is this notion of rectifiable curves.
Absolutely.
That's a much more sophisticated story. I mean, maybe we can talk over a coffee about it. Rectifiable is about how you can mimic a tangent space where there is no tangent space. Okay, it's not really about length. It's about, okay. So, but your question is important. I mean, after all, so when the curve is differentiable, of course, this answers everything. But clearly, I mean, after all, you know, I mean, you can imagine, I mean, you can certainly measure the length of a curve even in a non-differentiable world. I mean, okay, so that's a good question. Let's discuss it because I think it requires. Maybe I can write down a few examples of what could happen. Okay.
I think by definition, this limit converges when the function is of bounded variation.
Yes.
This is the definition.
Well, of course. I mean, you can, for example, play the game of.
And every bounded variation, we know how functions of bounded variation.
It's a bit subtle because, you see, when I said you can define the length of a curve even in a non-differentiable, you have to be careful. I mean, you can define the length of an object in the sense that you can find a suitable parameterization for which you can define a length. Yes. That's one point of view. I mean, but if you force me to take one parameterization, then so the problem is subtle. So what I'm saying is that maybe we should move on and remember for a good coffee, okay? Because now it really depends whether you are speaking of sets or of maps. And then it makes a big difference, okay? Okay, so this is the definition of the length. Now, why do I say this should be a geometric property? And actually, again, I know, don't be offended. In every lecture, from time to time, I will have to stop and say something, go back to real ground zero. But what is a geometric property? Now, this is an incredibly delicate question. Now, for those of you with passion of history of mathematics, I can tell you more or less we all agree with what Felix Klein wrote in 1872. Okay, the famous program of mathematics of Felix Klein. Every time you give a definition, essentially, of a type of objects, the first, actually, if you think back now, everything you did in algebra, in geometry, in analysis, the first thing you say, you define which objects are you studying, and which are the transformations between them. Study groups, okay. You define groups, and you define isomorphism of groups, okay. You define homomorphism. But then the definition of maps between these two objects automatically gives you a definition of isomorphism between these two objects. Because, okay, you say, I want a map from the space to itself, invertible, okay? So you have a notion of equivalence. You say, almost automatically, you should be able to say, I'm studying vector spaces up to isomorphism. So the sentence like a geometer wants to classify what it means. What does it mean? I mean, and then what is a property? A property is something which is invariant by the equivalence relations that you have defined. Now, this is very delicate because, for example, when you do topology, you study compactness. Is it a topology? Is it a geometric property? Is it a topological property? Yes. Because if something compact is homeomorphic to something else, the something else is compact. For example, okay, connectness is a topological property. But there are many interesting things which are not, actually. You have to be careful. Okay, so not everything is a property. So, and when I say what is the dream of every mathematician, the dream of every mathematician is to say, a compact topological three-dimensional manifold simply connected is the sphere. What does it mean, is the sphere? Hidden, there is the notion of equivalence that you are working with in that category that you are, okay? So when the first theorem I think we all studied it, of this type is a vector space, a vector space over the real of finite dimension is Rn. Then you say, no, I can write down infinitely many vector spaces different from Rn of finite dimensions. So what's the point is that they are isomorphic, not isomorphic as vector spaces. Okay, all this to say, remember, because actually it's going to be extremely interesting what is going to happen with curvature. I mean, when we apply this principle to curvature, things will be extremely interesting. I know that for now, but what does it mean now? What kind of geometry are we doing when we speak about curves and length? Well, if we are measuring the length, I mean, if we are speaking about curves, the only thing I need essentially is what is a smooth map. So I need a topology and a differentiable, blah, blah, blah. But when I'm studying length, I'm measuring distances. So actually here, this is a situation where I'm actually using the fact that R3 is a metric space. Up to now, I didn't care. But here, since I'm using this symbol, here I'm using the fact that R3 is a metric space, because actually here, of course, you could replace it with the distance, no? I mean, then the fact that it's the norm, as you know, that's an accident, okay? So we are using the metric structure of the ambient space. So what does it mean? That the length should be a geometric property, it should be invariant by maps which preserves the metric of the ambient space. Is it true or not? You see? So the first question is, well, okay, which are the maps from R3 to R3 which preserves the distances? It's like, I mean, you want to, and then the question is whether this definition is invariant under composition with these maps. Okay? Again, I'm not going to prove it because I think in some form you all know. I think the first time we see them in high school, in a way that it takes 15 years to realize. I mean, what they really wanted to tell us in high school. So, which are the isometries of R3 with the standard metric structure of R3?
Generated by rotations and translations.
In some sense, I said it at the beginning of the lecture, but I don't know if you are able to prove. Do you feel like you can prove it? It's a high school theorem, but it's quite sophisticated. I mean, so it's then of course you can also play with the linear algebra now to classify them in terms of matrices. So in that case, you can say first you have to prove they are linear maps, and then which lead up to translation. So there is a translation, a rotation, and a reflection. Okay, up to a translation. They should be represented by matrices with respect to standard basis, for example. So you can also, now you are older, you can say which matrices are good, and you find the orthogonal group, for example. Okay? So these are up to, so these are Rn in the sense of rotation, of translations plus orthogonal matrices. Okay. And now the question is, the length invariant by this type of operations? Of course, I'm going to write it directly. The answer is yes, otherwise nobody would have studied the length of a curve. Okay. But why is true? Well, because if I take a curve and I translate it and I compute the length, each of these things is not changed. So in fact, even the limit is not changed. So if I take something like this, so I assume there is no translation. If I rotate R3, each of these is not changing. If I reflect R3 through a plane, or whatever reflection you want to use, these objects are not changing. So in fact, it's not even this one which is not changing, it's that each of these is not changing. Okay, so it's particularly simple, but the principle is very important. Okay. Then second observation, which again, digging into the fact that now we are studying metric properties of curves. Another high school, I don't think actually, well, you use it every time, even in high school, but I don't think nobody claims to give you a proof in high school, is the answer to the most basic questions about curves and length. So give me 2 points. Which is the curve joining these 2 points of minimal length? Okay. Have you ever seen a proof of this?
Using Lagrange, Euler-Lagrange equation and calculus of variations.
That's one possibility. I'm not saying which proof, but have you ever seen one proof of this? Yes, okay. Segments, because actually there is even a direct comparison argument. Let me say, if it's not a segment, I can decrease. Even though, let me write down one line just to appreciate, I mean, this formula here. Okay, there are many ad hoc proofs. But I mean, suppose, what do I want to prove? I want to prove that if I have these 2 points that I already call alpha of A and alpha of B, even though I don't have alpha, okay? I have these 2 points, And I want to prove what? That alpha of A, so that any other curve passing through, joining these 2 points has length greater than or equal. Okay? So, just to appreciate a little bit of calculus here, I want to, it's just the fundamental theorem of calculus, no? Because I want to estimate this from above. So, okay, I just replace the this is the fundamental theorem of calculus. And now I just use the only calculus theorem. Okay, I can put the norm inside the integral. Okay, which is actually the length of alpha. Okay, so the segment has length less than or equal than any other length. Okay. It's a bit more interesting. It's a nice exercise to prove, passing through this way of reasoning, that actually if you have equality, because actually this proves half of the story. No? You say, if alpha is not a segment, the length is bigger. Well, I'm not sure if I said it correctly. Can you prove that if this is equal, then alpha is actually a straight line? Try. Okay. So a priori there could be another curve having the same length. You say, okay. All this leads us to the problem that we faced right from the beginning when I wrote the definition of a curve. The definition of a curve, I said it's very convenient, it's physically very adaptable and so on, but it leaves us with a problem from a geometric point of view. The same geometric object can be parameterized in infinitely many ways. And in some sense, since I'm a geometer, I don't care about the fact that the pendulum is moving on the straight line. I see a straight line, and I don't want to waste time in studying the pendulum going up and down, okay? So the basic question about all this story is also, another basic question is there a best parameterization? Give me a set, which is presumably the image of a curve. Is there a best parameterization of this set? Is there a canonical parameterization of this set? So I kill this kind of freedom of moving on these sets as crazy, arc, tan, log, sine, okay? And actually the notion of length is the one solving the problem for us. A little bit of notation again. So what does it really mean to reparameterize a curve? And in fact, what is a diffeomorphism? So this is a word which will enter often in other situations. A diffeomorphism now is just between two intervals. But this is a notion that we should start becoming friends with. So these are open intervals. I, J, or when I write these letters, these are open intervals. So this is a smooth C infinity map, invertible, with C infinity inverse. Okay, so this is like the notion of homeomorphism, but in the C infinity category. So instead of just continuous, I want everything to be smooth. Okay. Now, given, the point is that given, now in which way we are going? We have I, alpha, R3, and of course, as you can see, every time I have a diffeomorphism from J to I have a new curve. Technically speaking, is a different curve because it's a different map. Okay, so this is alpha composed phi. Okay, so this is another curve, but of course it has the same image. Okay, this is again passing from the straight motion to the pendulum. Okay, well actually the pendulum is not a diffeomorphism. Sorry, find an arctan. Okay, so So important observation. Do these two curves have the same length? Okay, between, of course, the corresponding point. Okay, because otherwise, if this was not true, this would be a tragedy for a geometer, no? Because that would mean that actually to compute the length of a curve, the same geometric object, the same set, has two different lengths depending on how I move on it. Of course, this is intuitively wrong, and in fact, it's wrong. Okay, so let's check it. Under these notations, pick AB contained in J, and let's give names. Suppose that, so now AB is in here, contrary to my previous notation. So AB is a compact interval here, so it's sent to some compact interval here. Phi of AB, let's give names, let's say this is CD, okay? So then the claim is that the length between AB of beta of alpha composed phi, just to be more explicit, and this is equal to the length between C and D of alpha. Okay, this is what I mean by the corresponding point, okay? Well, the proof of the claim is very simple. I shouldn't have erased this, of course, the formula of the definition. But what is it? How do you prove it? It's chain rule plus change of variable formula in the integral. I mean, but okay, I leave you as an exercise. Okay, we said the key. I mean, it's really a 2 lines proof. I mean, it's not. I'm not hiding. When something is complicated, I tell you. I'm honest with you. Okay. Very well. So this is all good. This means we have a notion of curves. We have a notion of length. This notion is a geometric property of a given curve, and it's also invariant by parameterizations of. So it's also a geometric. This means it's a geometric property of the curve, but here still it seems like it depends on alpha. And now I also notice it does not really depend on alpha, but only on the image of alpha. Okay? Now, we're supposed to finish at 10:30, is it right? So what do we do? Actually, this was important by itself, but it's also technically useful. Because we can do the following. So given the fact that the only interesting thing is invariant by parameterization, let's look for the canonical parameterization. Okay? And actually the length of the curve is solving the problem for us. So now pick alpha. And let's fix some base point on this curve. So always think of this picture here, no? So and let's say we fix only one point on this curve, T naught. I want to define a canonical diffeomorphism in some sense of the domain. So using exactly the notion of length. So I define S a map, okay, now it will be a little bit ambiguous. It's going to be at the same time a map and a parameter, okay, we will see. between I and a priori, let me just say R, and then we will have to decide where exactly it goes, but R, in the following way. For any time t, so for any time t, suppose actually I'm moving in this, I have another point, and I can measure the length between these 2 points. Okay? So I go exactly into the length between t naught and t of alpha, which, just for convenience, okay. Oh, very bad notation, sorry. Okay. Now, basic questions. So is this I mean, okay, at the end of the day, I would like to find conditions under which this map is actually a diffeomorphism, restricting to the image, okay? But, let's see, is it continuous? I mean, after all, we have to prove it's infinity, so we better start from 0. Why is it continuous?
The integral of is continuous.
It's the integral of, also, yeah, it's the integral of a function which is let's vote. No, you can be braver than integrable, come on. It's a bit more.
C1.
Okay, that's what I wanted. I mean, I wanted to split the class into 2 groups. Somebody said C infinity and somebody said C0. So, the question is, C0, you want to stay safe, huh?
Yes.
Okay, that's the only observation. This is not smooth. Because what is the norm of a vector? Now, every time you see square roots, you say, wait a moment. Of course it's continuous everywhere. So this object here is continuous, being the integral S is for sure C1, because I add 1 derivative. Okay. But is it C2? Depends. Depends whether the object inside the square root goes to 0 or not. Okay? So a priori, this is only, so the answer here is yes. You know, let's not play the game. Yes, C1, yes. C infinity only if, and of course the norm of a vector is 0 if and only if the vector is 0. Of course, for any t between whatever, I mean, on the domain of the V in I. Okay. So unfortunately, there is nothing to do. I mean, we have to assume. So from now on, well, definition. Let's give a name. Definition: alpha is called regular if the tangent vector is non-zero everywhere. Okay? And unfortunately, we have to start studying only regular curves. Okay, this seems a pity. It is a pity. I will comment on that maybe at the beginning of next lecture. Since we have 5 minutes, let me finish this part of the story. Because of course, every time you have to do a game like this, you wonder, how much am I losing? How many curves I'm losing? Okay, for example, in the examples we gave before, remember T squared T cube? T squared T cube is the prototype of thing that we are losing at this moment. Actually, I started from the most difficult case, because now here it's not clear, because of course here the tangent vector vanishes in this parameterization. But you see that actually being regular is not a property only of the image. Maybe, I mean, the difficult question is being regular a property of the image of the curve or just of the parameterization? Because think of a straight line. With uniform motion, is it regular? Yes, otherwise, I mean, if we are doing a geometry for which the straight lines are not contained, I mean, we should go to play football, okay? So, yes. But of course, what is alpha prime in the case of a straight line? Is the direction vector. If it's parameterized by uniform motion, is the vector v, I think I called it. No, it was v naught plus tv, so it's v. And v is non-zero, otherwise it's not a straight line, it's a point. Okay? But the pendulum, is it regular? No, because every time it stops. Basically, this is saying the point, if you are thinking physically, you are asking that the point which is moving on around does never stop. Okay? So there is a physical interpretation of this. Well, okay, I contradict myself. But this actually, so let's finish this problem. So is it really a big waste not to study non-regular curves? Well, not really. I mean, we can sleep well. Why? Because if there is a point where alpha prime, if there is an interval where alpha prime is 0, we are wasting time and we should be playing football. I mean, in that interval, nothing is happened. Alpha prime is 0, the point is not moving, so there is an interval where the point is staying there. So that's my definition of waste of time. Okay? So we can remove this. This is not adding length, it's not adding anything. I mean, there is a period of time where the point is there. Okay, let's remove it. Then what could happen? Well, it could happen something, for example, like this. Here there is not a period of time where it stays in the corner. Passes through the corner, stops, and moves back. So you say, well, so I cannot study, this has a famous name, this is called a cusp, for example. Or the pendulum, I have to avoid the pendulum, because actually even in the pendulum, it stops and moves back, but it stops it at one time, not for an interval, okay? But actually, if you think 30 seconds, the ones which are left, it's okay. It means that instead of studying this curve as one curve, we split it. So there is a point, we study the left part of the curve and the right part of the, and these two are two regular curves. So, okay, I mean, it's something I can sleep with, no problem. If I'm studying, if I have the pendulum, so now we are building a theory of regular curves. So you are telling me, okay, come on, I cannot use this theory to parameterize a pendulum moving in the universe. No, every time the pendulum stops, I stop calling it a curve. I mean, I take one period and I study that period. And then I take the next period and I study the next period. Okay? So, and they are joined together at points where nothing is happening because the point is stopping. So passing from differentiable curves to regular curves, actually, it's okay. You just have to be careful to apply your theory only if this is true, because actually, if not, the theory collapses. Okay? Okay, so under this assumption, everything works well. I mean, not just this map is C infinity, but automatically it's monotone. You see, the derivative, it has a sign, okay? Because it's the norm of a vector, so, okay? It's strictly positive, okay? So it's increasing. If it's monotone, it means it's also injective. So if I restrict to the image, I can also invert it. There is certainly an inverse. And the question is the inverse again C0, C1, C infinity? And the answer is yes. Because the derivative of the inverse, you can relate it to the derivative of the original thing, and this object is always non-zero. So now, under this assumption, S is actually a diffeomorphism between the original interval and some other interval. Okay? So that's the moment to stop. Now the question is, how can we use this? Actually, this object here is called the arc length, of course. So S, the map S, is called the arc length of alpha. And notice, just to finish, that this depends only on one thing. I mean, of course, it depends on alpha. But on alpha, the only thing that we did was to choose one point. So in some sense, it's unique up to the choice of this. But if I had taken another point, suppose you prefer another time as a starting time. Because this is, I will call it the starting time because how much is S of T naught? 0. So this is actually a point where this map goes to 0. If you prefer another T1, what is the relationship between my arc length and your arc length?
Constant.
It's just translating by a constant, because of course the integrals have the additive property. So I'm integrating between T naught and T, you're integrating between T1 and T, and the two things are the same up to the integral between T naught and T1, which is decided at the beginning of the story once for all. Okay, so up to the translation by a constant, this is unique. Good. We will meet on Thursday. Questions? I'm pretty sure you all knew everything we said today. I think what you have to start learning a little bit is kind of a critical interpretation of what you knew. Because I promise it's going to be very delicate when we go to other things.